The eruption of the Hunga Ha'apai volcano in Tonga sent literal shock waves around the world. It's understood to have been the most explosive eruption in 30 years, and created a larger tsunami than experts thought possible. Much is still unknown about the eruption, and scientists believe it's far from over. But already, it has scientists reviewing the thinking around the impact such a volcanic explosion can cause. Hunga Ha'apai is a very active volcano. Located about 65 kilometers from Tonga's main island, Tongatapu, Hunga erupted several times in the 20th century, and most recently in 2009, and then again in December 2014 and January 2015. The most recent eruption began on December 20th. The explosion could be heard from 170 kilometers away, and a large plume was visible from the Tongan capital, Nuku'alofa. Activity died down in early January, but kicked off again on January 13th, when a large ash column was sent 17 kilometers into the atmosphere. 2 days later, on January 15th, a far larger eruption took place. The event literally touched every corner of the globe as a pressure wave spread out in all directions to complete a full circumnavigation. Scientists, of course, are now asking themselves why the eruption was so powerful. They also want to understand how the tsunami was created. The answers to both these questions feed into future hazard preparedness, although to be honest, right now, these finer details are much less important than the immediate needs of nearby islanders. Their lives have been upended by catastrophic flooding and ash fallout. Nonetheless, scientific insights will emerge. They're already being assembled. The name Hunga Ha'apai, HTHH, refers to the two island structures that stood about 100 m above the Pacific Ocean surface, roughly 65 kilometers north of Tonga's capital, Nuku'alofa. What wasn't apparent to the casual observer was the hidden edifice below water, a volcanic mountain rising some 1,800 m above the seafloor. The HTHH Islands represented just the uppermost part of the rim of a caldera, the opening to the volcano that was 6 kilometers across. It was in this submerged caldera that gas-rich magma came into contact with cold seawater to devastating effect. For Professor Shane Cronin, from the University of Auckland, who's made a detailed study of this volcano, the water depth was critical. The caldera summit is about 150-200 m below sea level. That's just about the right depth for there to be quite strong, explosive interactions between the magma and the seawater. Once you get much deeper, then what tends to happen is there's too much seawater, and it suppresses that explosive activity. Professor Cronin said a big event had been due. The last major eruption was in the year AD 1100, and prior to that there was a major episode 1,800 years ago. On that basis, the repeat cycle was roughly 900 years. That's now. The tsunami that followed could have been created in several ways. In the near field, where waves over 1 meter high were recorded at the Nuku'alofa tide gauge, some component would have resulted from rock and ash initially thrown high into the sky, then descending back down into the ocean to displace its waters. What scientists can't rule out at this stage is whether the extreme energy in the event didn't also cause some kind of submarine flank failure on the volcano. Something similar occurred at Anak Krakatau in Indonesia in 2018, although that involved a large amount of material above water then becoming submerged. This is a possibility, for sure, commented Dr. Vicky Farini from Columbia University's Lamont Doherty Earth Observatory. In data we collected in 2016, you could see a lot of big solidified chunks that looked like they had slid down the side of the volcano in the past. So, with an explosion of this size, you certainly wouldn't be surprised if further large sections of consolidated material had moved. The good thing is we have the baseline data to make a comparison when we go back in, but only when it's safe. For far-field effects, there is a lot of discussion around whether that shockwave could have contributed to the run-ups recorded in New Zealand, Australia, and at beaches and inlets along both North and South America, and in Japan. The idea is that the sudden change in air pressure punches down on the surface of the ocean. This can change the elevation in the ocean by millimeters to centimeters, and when this gets closer to land, if the conditions are right, it can generate tsunami. We know this happened, for example, in the Great Eruption of Krakatoa in 1883, said Professor Dave Tappan from the British Geological Survey. We're working on it right now. Fortunately, over the past 20 years, we've developed the mathematics to numerically model these events to better understand them.